Dipole moments, deciding if the molecule is polar. The goal of this podcast is to take our knowledge of polar bonds along with our knowledge of how geometry works and decide if actual molecules are polar as opposed to just the bonds that we've done before. So first, let's talk about what a dipole moment is. A dipole moment is technically a vector addition of the magnetic moment of polar bonds. So what does that really mean? So let's take a one bond molecule first. So in other words, two atoms with one bond. If the bond is polar, the molecule has to be polar. So that would be something like HF, where we have hydrogen and then we have fluorine, the most electronegative element. And we know that that bond is polar. And since that bond is polar and there's just the one bond, the whole molecule will be polar. There's two different ways of writing it. You can write it with this plus and minus notation that we have here and here, or you can do this arrow with a plus side, and the plus side goes on the plus side and then across. Now, in multi-bond atoms, you need to look at the geometry, and this is because sometimes these bonds can cancel. So let's look at something like ClF3. So you may have to pause, pull out your model kits or your toothpicks and candy. Think about what this geometry really looks like. So when you write out your Lewis structure for this, you see that you have two lone pairs here and here. And so overall you have this T-shaped molecule. Okay, so let's look at the polar bonds and look at the directions and see what cancels out. And this is what they mean by vector addition. So we know that each one of these bonds will be polar, so we have three polar bonds. Now, if we take all of these vectors and we add them up together, what we can see is that some of these top two, top and bottom ones, these two, are going to cancel out. And so what ends up happening is these cancel, the up and down part, the vertical part, and then this whole horizontal part doesn't have anything that cancels it. So the total overall dipole moment will be this way. So this is still polar, the ClF3, it's a polar molecule, and we can draw the dipole moment in as going this direction. Now let's do some more practice with these, and I'll show you through these examples how you can end up with structures that don't actually that does not have a dipole, even though they have polar bonds. So these are the applicable ones that we've been working with. So let's start with N2. So we know that it doesn't have any polar bonds. Since it doesn't have any polar bonds, it's not going to be polar. If you have a molecule that has all nonpolar bonds, you can go ahead and say that molecule isn't polar. Now we have XCF4. So let's look at XCF4. So this is the non-ionic version. This was the one without the electrons removed. Now we had a square planar shape. I have it drawn here in sort of a way that says that it's 3D, but you may want to build this for practice too. So you have this square shape, and we know that each of those bonds are polar. Fluorine is very electronegative, Xe is not. So the fluorines are going to be taking all of the electron, or not all, but a lot of the electron density. So in this case, we don't have a dipole. And why would that be? Well, we look at all of those directions that those arrows are pointing, and they directly cancel out. So one of the ways that I like to look at this, and students seem to find helpful, is think about what would happen if you had that person, if you took this Xe and you put like a person there, and then you tied ropes to them and four different people pulled in each direction. And you'd see it all cancels out because everyone would be pulling in exact opposite directions. And so there's no dipole. Now let's look at the next one. So we have F6, and we remember from our discussion on the geometries that this was octahedral, both electron and molecular geometry. If you don't remember how we got that, just go back and revisit the geometries video, and that'll show you how to do it. So you have octahedral. Now think about what that looks like in 3 dimensions, right? And again, go back and visit the other video if you need to. So if it looks like it's in 3 dimensions, all of the fluorines are coming off at exactly 90-degree angles, and they're all pushing on each other exactly equally. So even though each one of these bonds would in fact be polar, because they're all going in opposite directions, we won't have a dipole. All right, now let's do another one. So this one's a little bit trickier. So we have this shape. We have 4 things attached to the phosphorus, which means we have a tetrahedral shape. Now, remember what that looks like in 3D. If you need to go back in the old videos, feel free. So we have this tetrahedral shape. And all of the bonds are polar. Now, interestingly enough though, they are not all the same atom, right? Now, since oxygen and chlorine don't have the same electronegativity, that changes things a little bit. If we were to look at this and we say there's a polar bond going this way, this way, this way, and this way, and again, you're putting that in 3 dimensions, so they're all coming out of each other equally at 109.5 degrees or so, they would all cancel if all of those were chlorines, or if all of those were oxygens, or if all of those were the exact same atom. These would all cancel out and you wouldn't have a dipole. However, in this situation, they aren't the same. The chlorine has a different electronegativity than the oxygen. The oxygen is much more electronegative, and so they're not all going to cancel. And so, yes, here there would in fact be a dipole. Now let's do another example. This is a little bit more complicated than the other ones we have too, and further drives home the same kind of principle that we were talking about with the POCl2. 3. Okay, so let's draw the Lewis structure for this first. Now, when we go to draw the Lewis structure for this, there's a couple of different ways that we could draw it, and in this case, they're not the same way. So we could do this and we could say, well, here I have 2 chlorines, 2 fluorines. Now these little dotted lines, there's dashed lines, that indicates that it's going back into the screen. These shaded in areas point out that it's coming toward you or out of the computer. So if we instead put the 2 fluorines going to the back, these are not actually quite the same molecule. They're a little bit different, and we would get different answers depending on how we draw it. So let's look at this a bit more. So here we have our dipoles for chlorine, and we have them for fluorine too, but fluorines are going to be a lot bigger. So here we have a little bit of a bond moment right there, and a little bit of a bond moment here. Here we have much bigger ones. Now on this one, this chlorine and this chlorine are going to directly cancel out, and this fluorine and this fluorine are going to directly cancel out. And so even though all of your bonds are polar, and even though some of them are different sizes than the others, they still cancel because of how they're oriented. Now let's look at this one. So here we have the 2 fluorines and the 2 chlorines, where the big, larger bond moment is going in the same direction back now. And then here, the smaller ones are going into the same direction forward. Now, some of them would cancel, and so the side to side here would cancel, and the side to side here would cancel. The side to side here would cancel, and the side to side here would cancel. But they're not going to all cancel equally. And that's because this direction, this coming out of the board at you direction, that is smaller than the moment going into the board or away from you. And so because of that, the overall dipole is going to be in the direction right in between these 2 pink fluorines. The side to side cancels and it puts it in this direction. Now, again, you can kind of think about this in terms of what would happen if you had somebody sitting in the middle with ropes tied to them and people were pulling on them. So you could make this out to be the really strong people pulling really hard, and this maybe, you know, hook up some like 5-year-olds or something pulling the other direction, trying to pull but not really being able to. You know, overall, which way would they move if you did that? And of course, they would move in the direction of the 2 strong people pulling them. So that's a good way to visualize it a little bit. It's obviously not 100% accurate with how the chemical stuff works, but it does help you remember it. Okay, so here your right and lefts are going to cancel. Your blue forwards will cancel with some of the pink, but not 100%. So the total dipole is going to be going backwards in between the 2 fluorines. Okay, so after watching this video, now you've been able to take your knowledge of how polar bonds work, take your knowledge of how the geometry works and how to decide on geometry, and combine the 2. So you're also starting to see now this building on each other, right? We build on the complication quite a bit here. So if you don't have your geometries down pat, you're going to have a very, very hard, if not completely impossible time with this section. So make sure you go back and work through the geometry work and play around with your toothpicks and candy and see how you can do so that you're able to go on to this section well.